Okay. All right. So I'm going to warn you, and I'm going to warn all of you that may be listening to this recording. I am very tired, so I don't know what's going to happen. It's going to be awesome, though. Okay, so again, this is lesson 7, and it's called stoichiometry. And it corresponds to chapters 10 and 11 in the text. All right, the first question we're going to deal with is this. How can we use the balanced formula? So we spent lessons 8 and 9 from the textbook, and our lesson 6 just balancing chemical equations, right? I know it was a couple weeks ago because we had a lab that I messed up for all of you. By the way, it was confirmed I totally messed it up. It was really bad. My math was horrible. It was Monday. I'm sorry. Because we redid it on Wednesday and it totally worked when I took some time to redo the math. I'm sorry. But we'll redo it. It's okay. We'll make some time when we do our next lab to redo this one so that it works and that you all can experience that reaction. But yeah, we spent 2 weeks ago our time just balancing formulas. And the question is why? Like, what do we even do with this information? Why do we care to balance the chemical equation? I'm glad you asked. And this is why. Wait. So the coefficient in front of anything in our equation, the coefficient in front of the reactant or the product, it provides it tells us the amount of material that we need to make that reaction work, or the amount of material that's going to be produced by that reaction. And so balancing these reactions tells us everything that we need to know about if we want this reaction to happen, how much reactant do we need, and if this reaction happens, how much product is going to be made. All right? Does it make sense? We did this a little bit in our lab, right, where we had our reaction of, let me draw this reaction again to jog your memory. We had sodium hydroxide plus hydrochloric acid produces what? You remember this from our lab last week? Salt and water. So salt water, and this is balanced. All of the coefficients are 1. And so we used this last week to say, okay, if we're going to react all of our sodium hydroxide, how much hydrochloric acid do we need, right? And since there's a 1 written here, there's also a 1 written here. If we are going to react 1 mole of sodium hydroxide, we need 1 mole of hydrochloric acid. Okay. The unfortunate thing is my math for what the mass of 1 mole of hydrochloric acid was not good. So our equation didn't work, okay? So we can take these, so we can use these coefficients to convert between any of our reactants, or to convert between reactants and products, or convert between any of our products. So if we know how much of one of these pieces we have, we can figure out how much we need or how much we'll make. And all of this is just like, yeah, so what, who cares? Let's do it, Dr. Engel. Let's work out some of these problems. I totally agree. So I made 3 of them for us. But they all use the same reaction, and they use a reaction that we've already gone through the effort of balancing before. Okay? So we're not starting anew, right? Okay. What I want you to do is over to the right where you answer these framing questions, I just want you to write watch and see. Watch and see. S-E-E. Watch and see. And then it'll drive you to look to the following equations. All right, you ready? First problem. How many moles of oxygen are required to fully react with 1 mole of glucose? How many moles of oxygen are required to fully react with 1 mole of glucose? Now this is an equation that we have balanced before. C6H12O6 plus oxygen produces carbon dioxide and water. Okay? We've balanced this before, and so I'll show you these numbers in case you've forgotten. We don't need to go through the effort of balancing this again. Okay? Now it's balanced. If you don't believe me, you can go back and check your material from a couple of weeks ago when we balanced this. Okay, so how many moles of oxygen are required to fully react with 1 mole of glucose? All right, and here's what we're going to do. So what I want you to do is get into the habit of figuring out how many transitions we're going to need to figure out this problem. Okay? Do we have the ability to convert from moles of glucose to moles of oxygen? The slide before just told us we could. Let me show you this slide again. We can use the coefficient to convert between reactant amounts. Here's one reactant, here's another reactant, right? Or we could use it to convert between reactant and product. And then what's not stated, but we could also do, is to convert from one product to another, although that we rarely do that. Okay, so can we convert from moles of glucose to moles of oxygen? The previous slide just told us we could, right? Okay, and so we should be able to do that, and it's only going to take us one step because the previous slide told us that we can convert between any of our reactants. Okay, and so we're going to draw a vertical line for every step required in that process. This one's going to require only one step. One step. Like, cool, what do we do with this vertical line? I'm glad you asked. Okay, so this vertical line, again, it's representing one step. We can convert from anything in our equation to anything else in our equation in one step. Then we're going to draw a horizontal line to cut our vertical line in half. And you'll see where this will start to be valuable when we have more than one step, which we'll come to very shortly. We'll have 3 problems where it's just one step, and then you're going to be like, Dr. Engel, this is way too boring. We need more steps. And then I'll give you 2 problems with 2 steps and 1 problem with 3 steps. And you'll love it. Okay? All right. For every step, and in this case we have only one step, right? In the top left, we're going to put what we're starting with. Okay? This problem gave us one piece of information. It gave us 1 mole of glucose. Do you agree? So what we're starting with is 1 mole of glucose. Okay? So again, for every step, we're going to put in the top left what we're starting with. The only thing we're given here is 1 mole of glucose. On the top right, we're going to put, for every single step, we're going to do this. I know right now there's only one step, but soon there'll be more. For every step, we're going to put what we want to go into on the top right. What do we want to go into in this problem? What's the problem asking us to find? How many moles of oxygen are required to react with 1 mole of glucose? So we're going to put moles of oxygen. On the bottom right, we're going to put the same material that was in the top left. Moles of glucose. Okay? And again, it seems weird initially, but hey, it's got a weird name, right? Stoichiometry. And it'll get less weird the more you do it. Okay? And then we need to put our conversion factors. For every 1 mole of glucose, how many moles of oxygen are required? For every 1 mole of glucose, there's a coefficient of 1 there if there's nothing written. It requires 6 moles of oxygen. Okay? And now we're going to treat these like 2 fractions, and we're going to multiply them across. So this is over 1. We left that section blank, so that's just over 1. We can cancel these units. This one right here has moles of glucose on the top of our fraction. This has moles of glucose on the bottom of a fraction, right? So those will cancel out, and we'll be left with the only units we'll have are moles of O2. And what's 1 times 6? 6. What's 6 divided by 1? 6. Okay? So this one, it ended up working out pretty easily because we were just doing 1 mole of glucose. We'll do more than 1 mole of glucose in our next problem. Okay. Does this make sense? It's okay? So we're going to raise the difficulty a little bit. You ready? Okay. No? Okay. So how many moles of oxygen are required to fully react with 5 moles of glucose? How many steps is this problem going to take? Can we convert from moles of one reactant to moles of another reactant? Yes, we can, right? The first slide told us we can do that. So how many steps is this going to take? 1 step, and I told you the first 3 problems are all only going to require 1 step. Okay, so we'll have 1 vertical line because we're going to carry this out in 1 step. We'll put our horizontal line. What goes in the top left? Moles of glucose, the only thing that it gives us. And how many moles of glucose? 5, right? Now we want to know how many moles of oxygen are required to react with 5 moles of glucose. What goes in the top right? Moles of oxygen, what we want to go into. Bottom right, we're going to carry this same material over. Moles of glucose, C6H12O6. And then we need to put in our conversion factor. For every 1 mole of glucose, it requires how many moles of oxygen? 6. Now we'll treat these like fractions and we'll multiply them across. We've got moles of glucose on the top of a fraction, moles of glucose on the bottom of a fraction. They will cancel out. And then we will multiply across. What is 5 times 6? 30. And our only units left are moles of oxygen. So how many moles of oxygen are required to completely react 5 moles of glucose? 30. Okay? That make sense? A little bit more complicated, but not much. Okay? Still completing it in a single step. The next one I want you to work on for a little bit before we solve it together. Any questions on this before we move to the next one? Okay. How many moles of oxygen are required to produce 5 moles of carbon dioxide? The balanced equation is up here. So first you need to figure out how many steps this is going to require and figure out where all your pieces go. Maybe another minute or so. All right, how many steps is this going to require? Still one, right? I told you the first three would all require one, but even if you forgot that, you'll remember that our first slide told us that we could convert from the amount of any reactant to any other reactant. We could convert from reactant to product or product to reactant. Okay, so we're going to carry this out in one step. We'll draw our horizontal line. What's going to go in the top left? The only thing we're given, which is what? 5 moles of carbon dioxide. What's going to go in the top right? Moles of O2, which is what we want. Bottom right is going to go the same material that was in the top left, moles of CO2. And then we need to do our conversion factor. Okay? For every, according to our balanced chemical equation, for every 6 moles of carbon dioxide, we require 6 moles of oxygen. Right? Do you see those? Okay, now we're going to treat these as fractions and we are going to multiply them. Right now we have moles of carbon dioxide on the top, moles of carbon dioxide on the bottom. Those will cancel. We have 6 on the top and we have 6 on the bottom. Those will cancel. Be reduced to 1. Right? And then so the only thing we'll have left units-wise are moles of O2. And 5 times 1 is 5. So it requires 5 moles of oxygen to produce 5 moles of carbon dioxide. Okay? So are we okay with these one-step problems? Notice what was required for us to do these one-step problems. What did we have to do? We have to balance the chemical equation. Because the only way we can convert from one reactant to another, or from reactant to product, or product to reactant, or product to other product, is using these coefficients, okay, which are representing the number of moles. I guess they could also be representing the number of molecules, but it's fairly difficult to get a single molecule of glucose. Right? Like, what about just one little crystal of sugar? But you know better than that, right? One crystal of sugar is, I don't even know, probably 1 times 10 to the 15 molecules of glucose. All right. We're going to take it to the next step, right? We're not satisfied with one-step problems, right? You're not satisfied with one-step problems, right? Okay, so here's where we get more steps. When we ask questions like this. We're like, okay, well that's fine and good to know that it requires 30 moles of oxygen to react with 5 moles of glucose. But what does that actually mean as far as how much oxygen I need? A mole's a big number, right? True or false? A mole is a big number. Yeah, it's a huge number, right? And so, if you're anything like me, it's hard for you to wrap your mind around a number that big. But grams, that's a decent number. Okay, that's a number we can work with. All right, so how can we determine the amount of material needed in grams? Or the same thing, you could say the amount of material produced in grams, how much you should produce. So remember from a few slides ago that we can convert between any parts of a reaction using these molar ratios, right? We can convert from reactant to other reactant. We can convert from reactant to product. We can convert from product to product, product to reactant, right? We can do anything we want as long as we have those molar ratios, right? As far as you know. Did I tell you all Happy Monday? If I didn't, Happy Monday, by the way. I know some Mondays don't feel happy. In fact, most Mondays probably don't, but this one in particular. So using the molar mass of the material, which we can find using our periodic table, we can convert from moles of a material into grams. We've done this many times. Yes? We've done this in both our real labs so far. We've done it in several homework problems, converted from moles to grams or grams to moles, using the molar mass. So I know what you're thinking. You're like, Dr. Engel, let's use this concept to make these problems more sophisticated. Because I want to be able to visualize how much material this actually is. All right? So how are we going to answer this question? How can we determine the amount of material needed in grams? You can write watch and see, or you can just write use the molar mass. Or you could write use a periodic table. I'll leave that for you to decide which of those three answers you want to use. Watch and see, use the molar mass, use the periodic table. Okay, any questions on this? Okay. So, we have our next problem. It says how many grams of oxygen are required to fully react with 1 mole of glucose? Okay, how many steps is this going to require? 2, right? I told you the first 3 would require 1 step. The next 2 would require 2 steps. And the last one will require 3 steps. So this one is going to require 1 step to go from glucose, moles of glucose, to moles of oxygen. Right? Just like what we did in our first problem. So it's going to require 1 step to go from moles of glucose to moles of oxygen. Then we're going to require a second step to go from moles of oxygen to what? To grams of oxygen. Okay? Remember, the only way that we can convert from amount of one reactant to amount of another, or the amount of reactant to amount of product, or the amount of product to the amount of reactant, the only way we can do that is using the molar ratios. That's the only way we can convert from one material to a completely different material. And then to go from the moles to grams, we'll use in the molar ratio. All right, so let's do this. We've got 2 steps. What are we going to put in the top left of step 1? We're going to put what we're starting with at the very beginning, which is the only thing we're given. And what is that? 1 mole of C6H12O6. Okay? Top right, we're going to put what we're converting into in step 1. In step 1, what are we changing into? Moles of oxygen, right? You have to be very, very clear to say that you are changing into moles of oxygen. That's the only way we can convert from one material to another, is using the molar ratios. Okay? Using our balanced chemical equation. So bottom right is going to go this same material. So we'll have moles of C6H12O6 down there. And then here, we've already got this one set up for us, right? Top left is going to be what you're starting with. Top right is what you're going into. What are we going to go into in step 2? Grams of oxygen. Why couldn't we just go straight from moles of glucose to grams of oxygen? The only way we can convert from one material to another is using what? Molar ratios. So we can convert from moles to moles. We cannot convert from moles of one material to grams of a different material. Right? It doesn't make sense. So we got to go moles to moles, and then when we're staying within the same material, we can go moles to grams. Okay? Down in the bottom right, we're going to carry this material down, moles of oxygen. And then now we need to figure out our ratios. So we've seen this ratio before. 1 mole of glucose requires how many moles of oxygen? 6. Look at our balanced equation. 1 mole of glucose requires 6 moles of oxygen, right? That's our molar ratio. And then here, 1 mole of oxygen is how many grams? Now this is where we need our periodic table to figure out the molar mass of oxygen. It's 2 times oxygen, right? Oxygen's molar mass is 2 times basically 16. Was it 15.9999? How many nines? 3 nines. Okay, we'll say 16. 3 nines, that's absurd. Okay? 2 times 16 is what? 32 grams. So 1 mole of oxygen has a mass of 32 grams. Do you see where that came from? Okay. 1 mole of glucose requires 6 moles of oxygen. 1 mole of oxygen has a mass of 32 grams. Okay. Now we'll change these into fractions and we'll multiply them. We've got moles of glucose on the top. We've got moles of glucose on the bottom. Right? We've got moles of oxygen on the top. We have moles of oxygen on the bottom. The only units we'll be left with is what? Grams of oxygen. Why is that good? That's what the problem wants, which lets you know you set this up correctly. Right? And then we'll do 1 times 6 is 6. 6 times 32 is, I believe, 192. And then these are all 1 down here, so we don't need to divide anything away. It requires 192 grams of oxygen to react with 1 mole of glucose. It's a lot of oxygen. 192 grams. How many grams are in a pound again? I know this was a while ago when we talked about this. About 450. So this is almost half a pound of oxygen. That's a lot when this is a gas, right? Half a pound of a gas, that's a lot of gas. You ever tried to bottle air? You don't even have to try. You just stick a lid on the bottle and you bottle air, right? It takes a lot of a gas to get that amount. So it just gives you an idea of how much oxygen your body requires to metabolize 1 mole of glucose. 1 mole of glucose isn't that much. Okay? Isn't that much. It's maybe like a couple of Snickers bars. You're like, man, I took that down in 1 night on Halloween. Right? You required almost half a pound of oxygen to metabolize it. It's a lot of breathing. Okay? Does that make sense? It's not horrible, is it? No, you're like, no, Dr. Engel, this is the most amazing thing I've done in quite some time. I get it. I get it. We're so alike, you and I. I do this just to entertain myself and my children. We've been reading our kids this series about a classroom hamster named Humphrey. I don't know if you're familiar with that series at all. The first book is called The World According to Humphrey, and then it's like all of these things according to Humphrey. But anyways, we've been reading this series to our kids for, 6 months. And we're on book 11. Anyways, so we got a hamster. We got a hamster this last weekend, and what do you think the kids named it? Humphrey. They don't even know if it's a boy or a girl, but its name is Humphrey. And they give it to you in like the little cardboard carrier. And my 7-year-old reached in to grab it, to put it in his cage, and it bit her. And she looked at me, and I knew what had happened before she said anything, but she could not believe in her heart that her hamster would have bitten her. So she says, "Dad, the hamster did something to me, and I don't know what. I think he may have bitten me, but I'm pretty sure he didn't." And I was like, "Did it hurt?" And she's like, "Yes." And I was like, "Yeah, he bit you, but it's okay. Like, he's in this box. It's not like his normal box. He's scared. It'll be fine." So she goes downstairs, and just before she can even tell my wife what happened, she starts hyperventilating, crying. Like, and she's trying to explain to my wife what happened. And I end up having to go downstairs and tell my wife what had happened and talk Reagan off the ledge. And it's okay. Now, anyways, she overcame it. She held him later that day. It was fine. You don't need to worry about her too much. But I thought I would share that with you. I don't know why, but I felt like I should share it with you. All right. How many grams of oxygen are required to... Wait, this is the same problem. Oh, that's because I didn't go to the next slide. All right. How many moles of oxygen are required to produce 5 grams of carbon dioxide? It's a little different. How many steps is this problem going to take? It's going to take 2, because I told you that the first 3 problems would take 1 step, the next 2 would take 2 steps, and the last problem would take 3 steps. But you could also think about these steps. We have grams of CO2. We can't go from grams of CO2 to grams of anything else. The only way we can go from one material to a different material is through what? Moles, the molar ratios. So we know step 1 has to be to go from grams to moles. Right? We know that. And we're just like, cool, now we have moles of carbon dioxide. Is that what the problem wants? No, it wants moles of oxygen. So there's our second step. And we're going to do a vertical line for each step. We're going to give ourselves a horizontal line to write wonderful things on. All right, top left, what are we starting with? 5 grams of CO2. Thank you for whomever whispered that. So 5 grams of CO2. Top right, what are we going into in step 1? Moles of CO2. Because if we don't go to moles, we cannot convert to anything else in this equation. You have to go to moles. We can't go from grams of CO2 to moles of oxygen. But we can go from grams of CO2 to moles of CO2. And then we can go to moles of oxygen. But we'll carry this unit down here, grams of CO2. Okay, now in the second one, we already have what we're starting with in our top left. What are we going to put in the top right? Moles of oxygen, because in this step, we're going to go from moles of CO2 to moles of oxygen. We're going to carry moles of CO2 down here. And now what do we need? We need our ratios, right? 6 moles of oxygen produce 6 moles of carbon dioxide, right? 6 moles of oxygen produce 6 moles of carbon dioxide, according to our balanced chemical equation. And then 1 mole of carbon dioxide is how many grams? Well, 1 mole of carbon dioxide has carbon plus 2 oxygen, right? Carbon, according to our periodic table, has a mass of 12.01 grams. We'll call it 12. 12.01 seems a little excessive. If it was 12.4, we'll keep that 4. But 12.01 really is 12. Okay? Things like that, they should bother you a little bit. Okay? To be that specific when it's unnecessary. 15.999, it's absurd. All right? So we already decided that 2 moles of oxygen was 32 when we did this in our previous one, right? Each oxygen is 16. 2 times 16 was 32. Is it still up on the board? Look at that. We've already got the 2 oxygen. 2 oxygen was 32 grams. But we're 32 grams plus the 12 from the carbon for a total of how many? 44. Somebody check that because it's Monday. Is it 44? Okay. So 1 mole of carbon dioxide has a mass of 44 grams. Okay? Sound good? So carbon dioxide is heavier than oxygen. It's interesting. So if you were to put them both in a tank, which one would be on bottom? Carbon dioxide. It's heavier, right? Do you have this material that's, oh gosh. I think is it xenon hexafluoride? Anyway, so you know if you breathe in helium, it makes your voice really high-pitched. So there's a material, and I think it's xenon hexafluoride. But it's a really heavy gas, so it does the opposite. It makes your voice really deep. And what's so cool is you can fill a tank with it, like a fish tank, and it's so heavy that the air doesn't penetrate it at all. So you can actually have this tank that's full of a colorless gas, like the air is, and then you can set like a boat, and it'll float on top of it. And it's so cool. Like you could create the illusion of something. What's the term I'm looking for? Flying, but what's levitating? Yes, you can give the illusion. And I wonder if it's heavy enough that a hamster could float. Gosh, that'd be so cool to try. Because then if it wasn't, I mean, as long as it's not a lot of material and the hamster just fell a little bit, it wouldn't get hurt. But then I wonder what the hamster would sound like if it had just this really heavy gas. Gosh.
But would it still be able to breathe?
Oh yeah, but you wouldn't want to leave it in there too long because it needs oxygen. But absolutely, yeah.
Does that really answer the question?
Does this one?
Yeah.
The way we've set this up?
Yeah, because it's saying 40 grams of carbon dioxide, but we're trying to figure out how many moles of oxygen.
Right. So then now we can set these up as fractions and start multiplying it. Grams of carbon dioxide will cancel. Moles of carbon dioxide will cancel. And we'll be left just with moles of oxygen, which is what we want. Right? These 6's can cancel and reduce down to 1. And then there's really not much we can do with this. We can't reduce 5 and 44. We just got to do 5 divided by 44. Which is awful. I know. It's a terrible number. I made this problem up. I'm to blame. But 5 divided by 44. Do you see why I'm doing 5 divided by 44? Because 5 times 1 times 1 is 5. 44 times 1 times 1 is 44. So 5 divided by 44, and we get that this is equal to 0.11 moles of O2. Anybody get something different? Did anybody do this problem? Okay, you got the same thing? 0.11? So it requires 0.11 moles of oxygen to produce 5 grams of CO2. All right? Sound all right? We've got one more, and how many steps is it going to require? 3. What do you imagine is going to be part of this? How are we going to get that third step? Maybe grams to moles, moles to moles, and then moles to grams. That work? Okay. How many grams of oxygen are required to fully react with 5 grams of glucose? How many grams of oxygen are required to fully react with 5 grams of glucose? So I already told you that this was going to require 3 steps. And other than that, I'd like for you to take a couple of minutes and see how far you can get in this journey to answer this question. How many of you knew what stoichiometry was before you came in here? How many of you love stoichiometry? You don't even need to show me your hands, I know it. I can sense it. This, what we're doing right now, is stoichiometry. but I also have no idea what I'm talking about.
I couldn't even find it in the book. When I tried to look it
Yeah,
up.
I know, the book doesn't call it this because the book isn't as fancy as I am. Alrighty. Let's set this thing up. Alright, top left. So here's step 1, step 2, and step 3. Top left is what we're starting with. By the way, this is about as complicated as these problems get. It would be very unusual to find a problem that required more than 3 steps in stoichiometry. But we've got some other wonderful gems in chemistry that we can pursue. If you're like 3 steps, Dr. Ian, that's not enough. I'm way better than that. I understand. Well, maybe we could do some more difficult calculations if you want. All right, top left. What are we starting with in step 1? 5 grams of glucose. And we better be starting with that because that's the only thing the problem actually gives us. That's the only piece of information we have. And then what are we going to need to go into in step 1? Moles of glucose, right? We want to be in moles because that's the only way we can convert from one material to another is using moles. I will tell you that so many times your ears will bleed, but you'll never forget it, right? That's not true. Your ears probably will not bleed, and if they do, it's not a result of me telling you that. I just realized I said that and it's recorded. And if one of your ear starts bleeding, it's not my fault. Okay. So we're going to go into moles of C6H12O6. You're going to like this one because we're going to have to do a lot of math to figure out the molar mass of that thing. Oh, you're going to love it. All right, so then we'll carry this grams of C6H12O6 down. Now in step 2, we're going to do what we can do once we have moles. We're going to go from moles of glucose to moles of what? Moles of oxygen. The only way we can convert from one material to another is by using what? The molar ratio. Okay? We'll carry this moles of C6H12O6 down here. And then, so here we went from grams to moles. Here we went moles of glucose to moles of oxygen. Now we're in oxygen. And step 3 is going to be what? What are we going to go into? Top right. Grams of oxygen. Which is awesome for us to finish there on step 3 because that's what the problem wants. It wants grams of oxygen. We got to carry moles of oxygen down. And I know this is a very structured way to solve these problems. Please, always solve these problems this way. Makes it way less likely that you're going to miss something or you're going to set this problem up wrong, okay? And I know it's like vertical line for every step. And if you want to, you can just like run through the steps of what you would need to do, right? So figure out how many steps you need. If I didn't tell you, you need 3 steps. If you're going to go from grams of one thing to grams of something else, you're always going to need 3 steps. So you have to go grams to moles. Then you can go moles to moles and convert materials, and then finally moles back to grams. Okay? All right, now what do we need? We need our ratios. The easiest one is to put in our molar ratios. 1 mole of glucose requires how many moles of oxygen? There's a 1 written in front of the glucose in our balanced equation. What's written in front of oxygen? 6. Say it confidently. Okay, don't whisper it. 6. All right. Now this one we've already done before. 1 mole of oxygen is 32 grams. This one we haven't done before. Right? 1 mole, 180? Straight up? Oh wow, that's not so bad. Thanks for doing that for us. That was awesome. Okay. 180. All right. Grams of glucose cancel, right? We'll set these up as fractions and start multiplying them. Moles of glucose are going to cancel. Moles of oxygen are going to cancel. And the only units we will be left with are grams of oxygen, which tells us we set this up right because what do we want? We want grams of oxygen. Okay? And then we really don't have anything we can, I mean, we can maybe factor these down, 32 and 180, but like the amount of mental effort it would take to do that isn't worth it. We'll just multiply across and divide what's on the bottom. Okay? So 5 times 6 is 30, right? 30 times 32 is, what is that, 960? Is that right? Is that what you got? Maybe? Okay, 960 divided by the only number on the bottom besides 1 is 180. 5.333333. Everyone satisfied with that? Not that I don't believe you, but I want to do it myself. You're totally right. You're totally right. All right. We'll just call this 5.3, and we'll be done with it. I mean, you can put a little bar over this if you want to show that that thing is repeating. You're like, boom, 5th grade math. Remember that, nailed it. Look at this. This is so cool. 5 grams of glucose, 5 grams of oxygen, basically, right? It's totally coincidental that it happened that way, because it's not always going to be like, oh, you're like Dr. Eagle. I have the inside track to solve these problems. I don't need 3 steps. I'm just going to add a 0.3 repeating to any of these problems. Don't do that. Don't do that. It was just coincidental, but it is kind of neat, right? If you want to react 5 grams of glucose, it's going to require you basically 5 grams of oxygen. But the molar ratios are 6 to 1. You require 6 times as many moles of oxygen as you do glucose, but because of how much more glucose weighs than oxygen, they end up being about the same amount of mass. And then let me ask you a couple of questions before you all pack up. By the way, if you have your materials ready to hand in, slide them into your envelope if you have it. Make sure your name is on your envelope. And so those materials are worksheets 6, 7, 8, and 9. They are quiz 8, the quiz over lesson 8, which is our quiz 2, and they are the exam, which is over lessons, I think, 5 through 9. Which pulled in, one from the last unit. I told you that was going to happen. So, anyways, and then the second lab that we did, but the first one you did a lab report for. Okay. What if I asked you this? What if I asked you this question and I said, how many grams of carbon dioxide can we produce from 5 grams of oxygen? How many grams of carbon dioxide can we produce by fully reacting 5 grams of oxygen? How many steps would that require? 3. Because we'd have to go from grams of oxygen to moles of oxygen. Once we're in moles, we can go to a different material. You can only convert from one material to another using what? The molar ratio. And then once we're in moles of carbon dioxide, now we can go from moles of carbon dioxide to grams of carbon dioxide. Okay? And just because This is 6 to 6, right? Which is basically 1 to 1. Don't just assume that if you've got 5 grams of oxygen, you're going to produce 5 grams of carbon dioxide, because you're going to be wrong. Because carbon dioxide is heavier than oxygen is, right? It is. Same number of moles, right? Mole to mole requires the same amount, but carbon dioxide is heavier. So you're actually going to be able to produce a greater mass of carbon dioxide for the amount of oxygen that you reacted. And you're like, that's so cool. Where did that extra mass come from? Right? Because we're like, 5 grams of O2 is going to produce more than 5 grams of carbon dioxide. If you work the math out, you'll see it. If you don't believe me, do the problem and you'll see it. Okay? So if we react 5 grams of this and we produce more than 5 grams, where did that extra mass come from? Question is, where did this carbon come from? It certainly didn't come from here, right? There's no carbon in oxygen. Where did this carbon come from? It came from the glucose. That's where the extra mass came from. Some of that glucose gave itself willingly to produce the carbon dioxide. Or not so willingly. Yeah. All right? Questions? Eventually I need to do the gummy bear demo for you so you can see how violent this reaction can actually be when you carry it out like that rather than waiting for your bodies to do it. All right? You're like, I've seen how violent that reaction can be. Right? I've given a full-size Snickers bar to a child because you told me to. And I saw how violent that reaction could be. Didn't I tell you to do that earlier in the year? Yeah. All right. Well, we are out of time. Go ahead and leave your work in your